Good morning, everybody. Let's start. So, I hope that you had a good Easter break and that it was useful for you to let go a bit of the course material and let things sink into your mind. I will take the time to do a bit of recap in order to get you back into the mood and the mindset of the lecture. So we were in the middle of index construction, and I already introduced to you some of the techniques. So I'll reuse the first slides here that I already showed last week in order to recap what we did. I can't repeat it enough because this is so useful to get things sorted in your mind. So we had the standard inverted index. This is the one most important structure in the entire information retrieval lecture. You probably noticed that we've used it every single week. We've augmented it, we've improved it, we have modified it, we've tried to construct it in this very lecture. We've had search structures with hash tables and B-trees in order to be able to search for the terms in the index. We had tolerant retrieval when we managed to handle wildcard queries with star anywhere in the world as a joker. We managed to handle spell correction in the sense that it's okay if the user makes a few mistakes. And we've seen how to extend the index, for example, with supplementary indices like the permuterm index, which rotates all of the possibilities for the word, and the k-gram indices, which are able to retrieve a word, for example, for ET that contains the two letters E and T next to each other. So this is called k-gram. We've seen also by-word indices or k-word indices. I don't have them here. I just want to make you aware once more that the k-gram index and the k-word index, it's pretty much the same thing mathematically. The only difference is that in the k-gram index, it's about letters. It's about pairs or triples or tuples of letters. In the by-word and k-word indices, it's about tuples of words. It's the only difference. But mathematically, it's just a matter of changing the set that you are indexing between either letters, characters, or terms. We've seen the edit distance, the Jacquard coefficients, the soundex encoding, and then we've been through a lot on hardware. I told you a lot about all of these things, especially that when you have a disk, it's much slower than memory, so we prefer to do things in memory. But let me see if you remember. So I showed you two ways last time that you can build this standard inverted index if the data, the collection, is very large. And you cannot just do it in memory in the same way we did it in week one. So I showed you BSBI and SPI-MI, right? These are two techniques. So let me see if you remember here, with a simple question, the complexity of single pass in-memory indexing. So we've seen first BSBI. In BSBI, the idea is that we shard the collection into smaller splits, smaller chunks, and then we collect the postings, we sort them, and we write them back to the disk. And then we do it for every chunk, and then we merge them with a merge sort in the end, right? The problem is that it had a couple of drawbacks. One of them is that it was not optimal in terms of asymptotically, because we had a logarithmic component. You know that the most efficient sort algorithms, it's n log n, right? So we did have this complexity in n log n, and SPIMI is able to improve on that, and not only in terms of complexity, but that's one of the things. So how does it improve in terms of complexity? I will give you some time to wake up. or to wake up your smartphones. Let me start showing the answers. Does anybody need more time? Okay. Aha. That's actually a very good thing because it's an opportunity to remind you. The correct answer was actually the first one. The third answer is actually the complexity of BSBI. This is why. And BSBI, this is the one I gave you. But SPIMI, I think I did not, or very briefly give it to you. So let me get back to it. So this was the hardware. I will not come back on the hardware. I will just remind you that we encoded the terms as term IDs, meaning that this takes a lot of room, right? So we are replacing them with some simpler IDs, term IDs. And this is how we can fit more into memory during the index construction phase, right? So this is what we do in BSBI. This is what I told you. We shard the collection of documents into smaller digestible chunks in such a way that each one of these chunks can be done in memory, right? So the thing is, we process them, we write back to memory, and that's it. And then we sort and merge back to the disk, right? So this is what we already saw. So then I give you more details that I will not come back to. This is the merging algorithm in the end. By the way, you will implement it in the exercise session. This BSBI algorithm. So you will have really a first-hand experience. So this is the thing. This was the third answer. That's BSBI. That's not SPIMI. That's BSBI. And the T-log-T, it's very easy to remember why T-log-T was BSBI, because T-log-T, that's sorting. And BSBI, the S in BSBI is sort, right? Blocked sort-based indexing. So this is very easy to remember because I'm sure that we've repeated so many times that n log n is the best complexity for sorting that I'm sure you remember that, right? But then we had the SPIMI, which was an improvement over BSBI. And the idea is that we don't have to keep the term-to-term ID mapping into memory, because instead of processing the postings in memory, so the term document pairs, we directly built a smaller version of the standard inverted index, but just for that one shard. That's one of the major differences between BSBI and SPIMI, is that here we directly built the standard inverted index. And then at the end, so we write them back to disk, and then we do the final merge. But here you see the difference. We don't have term IDs here. We really have the terms, directly the terms, right? And so this means that it scales linearly. You know, there is no n log n or anything. It's just O of t, and that's it. And this you can remember as well, because SPIMI is single pass in memory index, single pass. This is where you have the linearity, right? So be SBI, S for sort, T log T, single pass SPIMI, O of T, okay? So this is why I included this smaller thing here, but it's not a log of T, it's a log of D, right? This is why I said O of T. There is no sorting involved. Okay. So this is what I introduced last week. Let me see if I had another question on that one. Yes, I had another one that is still related to these two ways of building the index, BSBI and SPIMI. Why are we even doing that? And with what I've already repeated you today, now this should be easy to answer to this question. So the question I'm asking is very simple. Why do we even bother designing BSBI and SPIMI, right? Why did we bother do that? Because in the first week I showed you the standard inverted index. You even implemented it in Jupyter notebooks. You implemented the standard inverted index. So we've already done index construction in the first week, right? So why do we even bother? Because if you think of it, what we could do is simply do exactly the same thing we've done in the first week of exercises, It's just that you use the hard drive instead of the memory, but you use exactly the same codes, the same algorithm that you've used, just reading and writing from disk, right? Okay, let me stop here and see what you've answered. Very good, perfect. So it means you got it. So this is technically not entirely wrong that you have to write in blocks to the disk, but it doesn't mean that you couldn't modify a bit of a block and write it back. So that's not something that would prevent you in principle for just using the disk. This says that this is just made up stuff. That it's true that memory space has increased a lot. I mean, now you can have memory of, I think, up to 4 terabytes of memory in some of the nodes in clusters versus disks of 12 terabytes. That's only a factor of 3. It's not that much, right? But still, there is more disk space than what you have in memory typically in terms of maximum bound. So nobody answers this. This is correct. It's absolutely because of the disk 6 and the time it would take to read and write from disk. This is just, you could do it, but it would be too slow. That was the correct answer. And this is also made up stuff. But apparently, one person has a good sense of humor. So let me continue with other techniques. There's 2 more. I already showed you BSBI and SPIMI. There's 2 more. One of them is MapReduce. And the other one we will see later is something more dynamic, like online indexing. So let's look at the third one. This is MapReduce. I already, I think, last week showed you a bit how MapReduce works on the examples, using this Pokemon example. The idea of MapReduce is very simple and very similar to what we do in BSBI and SPIMI. We still shard the collection, the inputs. And the general idea of MapReduce is that we have this scheme here where we have something done in parallel. We can map. Then we shuffle stuff around, and then we reduce. You can see that this part here is very similar to BSBI and SPIMI, the first part, because we did exactly that. But the second part is different, because we don't write it back to disk in the same way we did for BSBI and SPIMI with the final merge. We actually shuffle stuff around in the network and then have again a phase in parallel. And I will show you exactly how, right? So this is a difference. It's exactly the same thing as this, but shown in a different way. What happens in the way you do that? You will see it on an example. It's actually very simple. So what I've shown you is that this is what I did in another lectures class, is that you can have mappers that take the input data, so this is one shard, and they produce key-value pairs. MapReduce manipulates key-value pairs all over the place. So collections of key-value pairs. So here we do something that maps each different kind of Pokemon to a count here. And then we have the shuffling phase where we assign all of the ones that have the same keys to the reducer. And then the reducer does some kind of aggregation. Doesn't have to be, but in general it's an aggregation. And then in that case we just add them, and then we find 8. And this is correct. Why is this correct? Simply because we have the guarantee that all of the key-value pairs that have the same key, they will reach the same person during the shuffling phase. So we know that that number is really the total number, with nothing omitted. Okay? But now, we should do it with MapReduce, right? We should try to do it, to build a standard inverted index that way, right? And of course, it's slightly harder than just counting objects and doing an aggregation. So what we have as an input is this. This is the initial collection of documents, and this is the one we are going to shard into smaller pieces, right? Then we want some mapping phase. We will shuffle stuff around, reduce phase, and ta-da, this is what we would like as the end result out of MapReduce, right? So how do we do that? So first, I can't repeat it again, we shard the collection of documents. So far, it's the only proven way that we have found in order to deal with very large amounts of data that don't fit on a single machine or that take too much time to process. So we shard the collection of documents, and the mappers process the documents. What do you think a mapper is going to do? This is a shard of the collection of documents that we want to index for information retrieval purposes. So what do we do? What kind of key value pairs can we produce here? Anybody? Who doesn't know? So one person will not be asked, but the others, now I can pick one randomly because I assume that you know. So can you tell me what we produce as key value pairs? Can you give it a try? Not really? Okay. So let me tell you. It's actually, again, I have good news. It's not even something new. What is an example of key value pair that we've been seeing since week 1 and that we even have a name for? Yes? Can you repeat?
Document ID and the token.
Almost. There's the right words, so let me repeat. This is a very good opportunity to be very precise about the terminology. So you said document ID and token. So what you mean, I think what you have in mind is a posting, essentially. In essence, what you said is correct. We do produce that when we have a token, and a token is in the document. But you need to consider that a token is an occurrence in a document, right? Oh, actually, I think it's really so good that you did this, because I think I even have a question that I meant to ask later. Do I have it here? I may not. No, I think I don't have it here. I think I have it for next week. Auxiliary indices. Oh yes, I do have it here. So this is. I will keep it for later for a different reason. So, sorry, I'm taking my time because this is extremely important and I want to do this right. So the answer is, the key value pair is what we call a posting. And a posting is a term and a document, right? In practice, you use an ID, so it's the document ID. And for the term, we are going to use the term itself, but we've seen that for BSBI, we can also use term IDs. But what I'm saying here is that a posting is a pair given by a term and a document. In what we have seen so far, a posting corresponds to a token, because we have the set of words semantic. Each document is a set of words. So a token is when you have a document and you have this word appearing in a document, that is a token. So the token is not just the term, it's the term in the document. It's both of them. You have a token, you need a document in which it appears, hence the term that it is, right? So be very careful that for now, and later I will adapt this, a token corresponds to a posting, not to a term. A term, for an example of term is computer, right? But computer is just a term, can be in any document. But now, if I take the information retrieval book and I find in that book the word computer, this is a token, because that's a term in a document, really. So you need a term and a document pair. Who understood this? Great. So there is nothing new here, because in the standard inverted index, we have posting lists everywhere. And a posting is a pair made of a term and a document, right? This is what a posting is. And a posting corresponds, when we have the set of word semantics, to a token in a document. So now that this is clear, I'm coming back to the slide. And this is exactly what happens. We produce these postings. So for example, we may have two documents. It's a very simple example. In practice, maybe there's 1,000 of them in a shard, but we have two documents, the green and the red one. I'm representing the documents with ID, so we have document 1 and document 2, And for each token that there is in the document, so this is a token, it's an occurrence of ETH in document 1, then there's an occurrence of computer in document 1, data in document 1, information in document 1. So here we have 4 postings, right? And for document 2, we have 4 other postings with CPU, ETH information, computer. Again, notice that we have ETH2 and ETH1. It's the same term, ETH, but these are 2 different postings because here it's ETH appearing in document 2, here it's ETH appearing in document 1, right? Corresponds to a token if you look at the document and see ETH written on it. Okay, so as you can notice, a posting can be seen as a key-value pair. It's that simple. And we use as a key the term for reasons that will soon become obvious. So this should be really easy for you to understand because there's nothing new and we didn't even invent anything new here. So now the reducers. It's exactly the thing we've been doing before, meaning that we've had all of these postings that were generated in the previous phase, which are key value pairs with a term as a key and a document ID as a value. And I told you after the mapping phase, what do we have after the mapping phase when we produce the postings? What is the second phase of MapReduce? Starts with an S. Shuffling, when we shuffle all of the key value pairs around. So these key value pairs get shuffled around in such a way that all the key value pairs, all the postings corresponding to the same term here will be sent to the same reducer. So this reducer here is responsible for information, for the term information. So it will receive during the shuffle phase all of the postings that have the term information. Okay? So it receives them. What does it produce? What do you think it will produce? So when we were counting pocket, yes, can you tell me? Exactly. And what is it called? Yeah. So you are right that we produce a list of document IDs on the physical, in a physical meaning, because here, yes, absolutely, this is a list of document IDs, right? On the physical level, that's a list of document IDs. What this really is a list of postings. Because we have these postings here, information 1, information 2, so it's the same term appearing in many documents, so we have plenty of different postings. We sort them by ascending number of document ID, and then we arrange it. The fact that here we only list document IDs is only to avoid the repetition because it's the same term anyway. So why would we every time write information 1, information 2, and so on? We just write it once and for all on the left, the term, and then we list the document IDs. So even though you're absolutely correct that this is a list of document IDs, the name that we give to it is a postings list, because this can be seen here as the logical representation of that list. It's a list of postings, and this is the physical representation optimized where we only write the term once and then the list of sorted document IDs. For whom is this clear? Okay, so now it should be obvious. We have it, reducers take care of terms, so it doesn't have to be that a reducer has only one term. Maybe this reducer is responsible for like 50 terms, right? So it will produce 50 different posting lists associated with the term. And then that's it. You just gather everything around. Maybe one of the reducers produced these 3, and another one these 2, and another one these 2. But when you gather everything back, you have your final results. You have your standard inverted index. Who followed the MapReduce? Okay, very good. So I hope that now you understand the difference between the 3 that we've seen so far. Yes? In purple, right? In purple. Yeah. Can anybody answer that? Yes? Exactly. Also known as, there's even a name for that. It's the document frequency. And this we will see next week in details. We will actually, for now, I only told you it's here, right? But we never really used it. Next week we will use it, right? So this is it. This is our standard inverted index, okay? I wanted to show you a few more slides on MapReduce. For pedagogical reason, I'm showing to you version 1 of MapReduce because it's changed a lot since then. But you can see how it all works when it is in the cloud. There's actually one of the nodes that's known as the job tracker. And we have plenty of slaves here. It's a master-slave architecture, and we have the data nodes and the task trackers. So here I mixed two things. I mixed something called HDFS, which is a distributed file system where you have the files stored in blocks, very big blocks, hundreds of megabytes. And here we have the task trackers that are basically the mappers and the reducers. And the one thing that is such a brilliant idea about MapReduce is that we arrange things in such a way that we bring the query to the data, meaning that the document shards, the documents themselves would already be stored on the nodes, right? Nicely arranged in blocks. And the mapping, so the production of the postings out of the documents, is done on the same machine on which the documents are stored. We don't even send them over the network. This is why MapReduce works so well. So the storage and the processing happens on the same machine. So of course, when you have produced the postings, it's a different story. You need to shuffle them around and send them over the network, right? But in the initial mapping phase, you don't need any network in order to do that. Or pedagogically, I'm going to say you don't need any network. If you want to know why you actually do need some network, then just visit the big data lecture. So this is it. This was MapReduce. You don't have to know the implementation details of MapReduce. It's not part of the scope of that lecture. As I said, it's a different lecture. What you need to know is understand from a logical perspective what happens, how we map two postings, how we shuffle around the postings, group them by term, and then create the postings list for each term and obtain the standard inverted index. That's what you need to know. Okay, so this is it for the, I'm checking if I prepared any question for that one. So let's now look at the fourth way of building an index. We'll have 4 in total. The fourth version, with a few variants, is called the online index construction. Online simply means one thing, is that in the first 3 that we've seen, the documents are all given, they are stored somewhere, and that's it, and you need to index them. Online means that you may have new documents appearing, you may have documents getting deleted and so on, and you need to keep rebuilding or updating the index, the standard inverted index. So this is the one major difference of this fourth approach, because the documents keep coming or getting deleted. This is why it's called online. So what we can do is the initial construction of the index, so we may have some existing documents in there. Now new documents get added to the to the collection. So imagine that we have these documents here in green on the right, they get added. What could we do? What could we do in order to make it work? So this index is only on the blue ones, right? So if we continue to query, we will only answer queries with the blue documents. So what is the easiest thing that we could do in order to add these green documents to the index? The easiest thing, if you don't want to invent new things, you just want to reuse things you already know. What could we do? I'm really asking for a very simple answer. It's a very naive answer here. Yes? Exactly. That's exactly what the answer I was waiting for. You can absolutely rebuild the index completely from scratch. You throw away the old one and rebuild it, and then you have this new index, and you have these new postings here that use the green document IDs, so the new document IDs, and there you go. And that's totally fine. It is correct. You know that, excuse me, in general, when you want to implement a new feature or solve a problem in IT, this is something that is not necessarily, I mean, in some lectures you may see that, but this is something you will see later in the industry. if you want to invent something new, first implement something correct. It doesn't matter if it's slow, it doesn't matter if it's not optimal, start with something correct. And then worry about performance. So this here is the right first step to supporting online document processing, online index construction, because this is absolutely correct. We can just rebuild the index and that's it, and we've solved the problem, right? So now is the second step. Can we do better? Still correct, keep it correct, but improve the performance. So there's a few drawbacks, as you can imagine, for index reconstruction, because, yeah, that's just another slide to say that even more documents as edit. There's two drawbacks with this periodic reconstruction. The first one is that there is result staleness, meaning that when you reconstruct, you are not reconstructing every time a single document gets added. You may wait. For example, you can do it every hour, or you can do it every day, you can do it every 2 days. How much time does it take for a new, well, I think they've done better now, but do you know, let's say a couple of years ago, when you create a new website, how much time does it take for Google to index it? A few years ago, not today. Well, it was 48 hours. Typically, you would have to wait for 2 days. That's exactly because of this, because Google and search engines periodically rebuild their index, and it takes 2 days. They do it every 2 days, so it takes 2 days until this is done. So we have a staleness issue. And the other issue is potentially, except if you still keep the old index in the meantime, you may have an unavailable system if you just throw it away because you don't have space. Or even if you keep the old index, it could be slower because all the computing power that it takes to build the index, it takes resources, and you don't have these resources for querying. So you may have something slower. So you see, this is a correct way of doing it. You can reconstruct the index periodically, but we have the staleness and slowness issues. So we have an alternative that we can use, is that if new documents arrive, then you keep the old index on the disk right here, and you don't touch it. And the new documents that arrive, you consider them in a separate index in memory, much smaller. And this index, it's in memory, so it's very easy to update. All you need to do is append the document IDs to the terms that they contain. It's easy to do in memory. It's just list structure, linked list structures, and you can add new terms if you don't have them, update the B tree. We've seen all that. You just need to insert the term in the B tree, B+3, and so on. So this you know how to do. And the idea is that we have this auxiliary index. How can we now answer a query? Yes? Exactly. If we look at both indices, we can do the union and the text. So in that case, we would return this document here, these 4 documents, and this one. So we have 5 results. And what happens is that at some point, so you keep adding new documents, the auxiliary index will become too large. And then what you can do is that you can merge it back onto the disk, right? There is one condition that this is easy to do, to merge the auxiliary index onto the disk by just appending the new document IDs to the posting list. What is this condition? I'm assuming something, yes? Sorry, I didn't understand you. Yes, absolutely, you are correct. So here we have a sorted list of document IDs, so we are assuming that the new documents IDs are larger, right? This is something we can do. We just need to assign them so that it's an increasing document ID, right? So you are right. This is one thing. We need to make sure that we assign always higher document IDs. There is another thing that I wanted to hear, yes? Exactly. Yeah. Yes, this is exactly what I'm getting to, but now I want to express it in terms of disk. In memory, this is exactly it. We have a list, and we append something to a list, and a list can do that. But disks, they don't know about these things. The thing you have on disks, these are files. So what constrains do I have on the disk in terms of files for this to work? Can I append to a file? Yes, I can append to a file, right? So what constraint do I have on the way that this is stored in terms of files for this to work? Yes? Yes, you could also leave space in the file. I'm going to take the other alternative that you suggest. You append at the end of a file. So the idea is that if you manage to make it a file appends, an append to a file, then this will work, right? And for this to work, that's what I was actually waiting from you, is that each posting list needs to be its own file. If this is a file, then I can just append something to it. If, however, this is only one single file, then I can no longer do that, because this would be in the middle of the file. That would not be an append in terms of files. It would be an append logically, but in terms of storage on disk, that would be an insert, right? So who understands this? Okay, if we have single files, if every single posting list is a file, then that's a file append, and then it works. But the problem, before I get to that, I have one more question. That's another advantage, by the way, of the append, is that it's one seek per file. So it means it's linear in the number of terms to merge, because that's one seek, one seek, one seek, one seek, and then you just stream over the new document IDs. So this is very good, because the seeks are something that we are worried about in terms of disk access, and that's very good. Now, we've answered the question, what happens if a document gets inserted? We just add it into memory, and then we query both index. What happens if a document gets deleted? And this is a question that I prepared for you. Auxiliary indices. So we have our auxiliary index setting. We have a document on disk that is not touched, and we have some smaller ones in memory, smaller documents, smaller standard inverted index, that gets maintained. So we have these two indexes. How do we deal with the documents that gets deleted, that gets removed from the collection, right? So it should not be returned anymore by the query. So the first answer is we have an invalidation bit vector. I'm making up a lot of stuff in there, so you have to be careful even if it sounds very serious. You can remove them on the fly from the auxiliary index. What's the big deal? It's in memory. That's very easy to do. We actually don't really deal with them. We just let it be, and we accept a lower precision in the answers of the query. Or we just retrigger a whole-scale index reconstruction on disk, and that solves the problem. Okay, let me see what you answered. Yes, the first answer convinced you, and that was the correct answer. We have an invalidation bit vector. This doesn't work because the document you delete may be on disk. If it's in memory, yes, you can delete it from the auxiliary index. If it was a very recently inserted document, if it's a very old document, you would have to remove it from disk. This is why this doesn't work. The lower precision doesn't work because it's not a matter of precision. If the document is gone, then it's gone. It's not going to be that you return something, So there would be an issue. So you could argue that it's something, if I want to be precise, you could argue that it has to be with precision, because if you have a very basic implementation of the query engine, it may return by error this deleted document saying, hey, there is a result in there, right? But if you consider that you also want to display the results with the context of the document, like an excerpt of the document with a very nice highlighting on the words that you found, then maybe it doesn't work because the document is no longer here anymore. Right? So this is why it's not quite satisfying, this thing with the lower precision. It's not really satisfying. And the last one is, in theory, it's correct, but it's not practicable, and that's not the idea of the auxiliary index, because we want to avoid the drawbacks of index reconstruction. So this is the correct answer. We have an invalidation bit vector. If something gets deleted, we just marked it as such in the bit vector. This is indexed by document ID, so very straightforward. And when we have a query, we simply take, for example, we query it for ETH, and we have here the postings that are pairs with ETH and document IDs, and then we check against the invalidation bit vector like this, and we filter out anything that got deleted. We only let through the documents that are still marked as non-deleted in the invalidation bit vector. Okay? So this is how we deal with deleted documents. Okay, so we have something correct, something that's better than the index reconstruction, but there is still one thing that's not that satisfying, is that one file per posting list is not really practicable, in the sense that if you have a lot of postings, that's going to be a lot of files, and then the time that it takes is going to be enormous in order to do the merges. There is another issue. It's not just that it's going to be slow, it's that if you store it on a local drive, if you're just doing it on your own computer, and it starts to scale a lot, you have 1,000 files, millions of files, that's fine. 1 billion files, it will no longer work on your hard drive, right? Then you will need a distributed file system, and then it's a big data setting again. So you may have an issue if there's too many terms, you can no longer do it on a single machine anymore. And if you have thousands of machines, then maybe MapReduce will be a better option. So this is the decision spectrum that we have, right? Either we take this setting that I told you about where each postings list has its own file. This is one extreme of the spectrum. At the other extreme of the spectrum, we have one super big file that contains the entire standard inverted index, right? This is the other side of the spectrum. I think in the exercise, that's even how we will store them. It's going to be a big index with all the standard inverted lists. Or you can have something somewhere in the middle where you group some of the posting lists together, but you still have them in several different files, right? And this is usually a good compromise. But let's now just do some complexity analysis. Let's look at what happens with this solution that we came up with, that we have this index stored on disk that we don't touch, and the auxiliary index, and we periodically remerge the index on disk. If we have everything in a big file, this is what I'm thinking of now. Not one file per posting list, but one very big file. We have these incoming postings. It's the documents that get created, right? But with my glasses, I view incoming documents as postings lists, just the lists of the tokens that are in these documents. So we have the incoming postings. And if we have n, n is the size of the of one single standard inverted index. It's when we start hitting the memory, and the auxiliary index is too big, and then we merge. N is that number. N is the maximum number of postings that we can have in memory. So if we are limited by n, then we will have t divided by n merges, right? If t is the total number of postings, because every time we hit n, we merge. So that's just primary school math. It's a division. And then we will have all of this 1, 2, blah, 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 up to t divided by n merge. And we are merging the n postings that are in memory because the memory got full. So we hit that value of n, then we merge n, 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 and so on. So who understands this? Yeah. So you see, even primary school math sometimes can be a bit demanding, and even for myself. So let me go through this again. I am considering a setting in which I have postings that keep coming. But I'm the one who sends them, so I know how many there will be. Ultimately, there will be t postings, right? And I send them periodically. What happens? I start first with nothing on disk, and I build an auxiliary index in memory. The maximum size that it can have is n, the maximum number of postings. So once I have received these first n postings, my auxiliary index is full. The memory is full. I cannot build a bigger one, so I will write it to disk, right? And then the memory is empty again, I will start receiving the next n postings from my input stream. Then it is maintained in memory, and bam, for the second time, the memory is full. So I will merge again these n postings onto the disk with the n postings that are already there, and then delete the memory again. And I will do that how many times? Well, the total number of postings divided by the size of one single chunk that fits in memory, that's t divided by n, right? So I have every time n postings when my auxiliary index is complete, and that means that I have t divided by n instances of that merge, right? So who now is following? What's happening? Okay? So now I'm calculating the complexity of that. The first time that I will just write down my first auxiliary index to disk, it's n. That's the number of postings that fit in memory. It's n. The second time is 2n in order of magnitudes. Then 3n, 4n, and so on, and then finally t. Because here, the last time, you are basically merging absolutely everything, right? So here you have the whole t number of postings that get merged. And that's actually only logical. The more you have incoming postings and new documents, the bigger the index on disk is. So every merge will be a higher complexity than the former merge, right? So I have these complexities, and now all I need to do is add them to get the total complexity. So I will do this plus this plus this plus this, and so on. So I add them. So that gives me the overall complexity of dealing with all of this stream of incoming postings and to index them. This is my complexity. Right? Who is following? Okay. And now I will just do some white magic with the numbers here. I will first factor with n, just put it in parentheses here, and then 1, 2, blah, 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 plus t divided by n the last time. Okay? Then this is the sum of the k first integers. And as you know, the sum of the first k integers is, it should take you 1 second to answer this. What is the sum of the first k integers? Kk plus 1 over 2. This should be a reflex. You should know that by heart, right? Okay, so this is the sum of the first integers. Who knows that? You should. This is what normally you saw that, right? It's discrete math. So we have this, and then we just simplify, and this is, tada, the complexity that we get, right? So we have quadratic complexity in the number of incoming postings. That's not really so great. I mean, quadratic, usually we teach you in the algorithms lecture that anything exponential is very bad and polynomial is very good. But when we deal with large scales of data, quadratic is already what we don't like. We already don't really like quadratic stuff. So this is not really satisfying, as you can see, okay? If you still didn't get it, there is an alternate account of that in the book with a totally different arguments, but with the same results. So if you didn't quite understand what I told you, try the book. Try reading the book and see if this other angle to find this result explains it better. Okay, so we have this quadratic complexity. Can we do better? This is my cliffhanger for the break, because I just realized, because it's not ringing here, that we are already into the break. So I will see you at let's say, give you a few more minutes, at 17 past 10. So at 10:17 in order to continue. Okay, it's 10:17, so let us continue. So for this last part of the index construction lecture, we are online index construction. We've seen a first very naive method of just reconstructing periodically everything. Then we've seen a second method with the auxiliary index, where every time the memory is full, we merge it back. Can we do better? Because as I told you, we very much dislike quadratic things in large-scale database applications. Can we do better than that? The answer is yes, and I think I can even make you find how to do that if I try to reactivate your memory in terms of data structures. We have again some joke here. Who remembers when you have, say, a vector that is a an array that can grow. So you have, you keep adding things, and every time you allocate new memory when you append something to the array, right? So you've seen that in the algorithms and data structure lecture. I think I can safely assume that. But do you remember how the memory management is done here? Do we allocate every single time we add something? Do you allocate new memory for it, and that's it? Does anybody remember how this is done? Allocating memory is very costly, yes?
We usually allocate more memory than we actually need.
Yes?
Addition of data. So let's say every time we double allocate.
Exactly. You double every time. This is the one thing I wanted to hear. So actually, you will allocate once here, but when 3 arrives, you allocate the double size, and then when 5 arrives, you allocate already 8 here, and when 9 arrives, you allocate 16. So you basically double every time. This is exactly what we want to do here, because the t-squared here, it comes exactly from this issue. It's that in this first naive implementation of the auxiliary index, every time the memory is complete, we merge. And then it's complete, we merge. And then it's complete, we merge. But this grows only linearly. It's as if we were allocating the vector one cell at a time. This is where the t-squares comes from. So what if we could improve this auxiliary index, but having bigger and bigger and bigger and bigger indices on disks, not that wouldn't grow linearly, but exponentially in size. And exponential means that we had the very good idea of calling it logarithmic merging. We just take it upside down. And this is how it goes. In the book, it's only explained, I think, with a sentence with the first 2 steps and then and so on, but I wanted to make sure that I really explained the and so on very precisely, because this is not so easy to understand, but you will see it's also not so complicated to understand. So here it goes. Really, remember what we did with the vectors. The only thing I'm going to do now is double every time. I'm going to just be smarter. So n is still the maximum number of postings that fit in memory, t being the total number that I want to index. So what happens? I start with memory, exactly as I did with the auxiliary index. I have reached my size of n postings because enough documents have arrived. I call that Z0. What should I do when it's complete? I just do exactly the same thing. I write it to disk, right? This is what I do. And then I remove it from memory, right? So now I have n postings on disk. I call that I0, right? So Z0, what was here, and I0 is what is on disk, right? Here I have n posting, right? And the goal now is to make it double every time, in essence. So now I keep having its online indexing, so I keep having new postings coming, new documents being inserted to the collection. So again, my memory is feeding, and bang, I have again n different postings. What do I do now? And here it's still the same as what we've seen before. We merge it into 2 n postings, double the size, right? And then we write these 2 n postings in memory. And then, again, new postings arrive. Up to this point, right now, what you've seen here is exactly the same thing as we've done before. We have had the memory full once, written to disk, the memory full a second time, merged into a 2n sized index on disk. But now it's different. Because now my memory filled again with n postings, but instead of merging it here into 3 n postings, I will leave that alone, and I will simply write this back to disk. Just write it to disk, right? And now the memory is filling again. So how many indices do I have now? I have 3 indices. How do I answer queries? By taking the union of these, right? So I just have to look at more than 2 indices, just keeping in mind for later. But now I have this index I0 of size n and I1 of size 2n plus the newly arrived postings in memory that are here. So now it's full. What should I do? Well, I will merge it with the index of size n there and get a second one of 2n postings. But again, merge it there with the one on memory and get how many postings? 4n, and then write that back to disk. So you see now we double every time, right? Now I have 4n postings on disk. Again, new postings arrive, I write them to disk. New postings arrive, it's already on disk of size n, so I merge it and write it to disk. Again, new postings arrive, I write them to disk. Again, new postings arrive, there's already I0 on disk, so I merge it. Here I want to write it to disk, but there's already I1, so I merge it again. And here there's already I2, so I also need to merge it again. But now by the time I do that, you understand how it's going on, right? You understand what's going on every time. I basically maintain a number of indices here that are growing exponentially in size. N, 2n, 4n, 8n, and so on, and so on. So I have this very quick question to check that you followed what I've just told you. And it's this question here. You know that I call them I0, I1, I2. It's the name that I gave to the indices on disk. Let's say these are files. There's a file I0. There's a file I1 containing the inverted index for 2n postings, and so on. So now, imagine that somebody is executing this algorithm, the logarithmic merging. Documents keep arriving, and they implement this thing with merging on disk, merging with the disk, writing back the merge, and so on and so on. It's exactly what I've shown to you. I'm giving you 4 different snapshots. In the first snapshot, there is only a file I0. In the second one, there's a file I0 and a file I4. In the third setting, there is a file I1, I2, I3, I4. And in the fourth setting, there is a file I0 and I1, I2, I3, I4. Which ones of them can actually be seen? Which one of them can you actually observe if you take a snapshot of the disk during this construction? So you have to select them, or maybe none of them is consistent. None of them would ever be seen on disk, or all of them are consistent set of files that you could see on disk during this process. So it's basically what can you see at the bottom of the screen of what I've showed you. What is a consistent set of files that you can see on disk. Okay. Let me see. You can still keep voting. Very good. All of them are consistent. This is absolutely true. So this is consistent, this is consistent. This is also consistent because, remember, it's the first time you do it, the first time you write to disk. That's exactly what you see. You have I0. This is consistent as well because you can keep going. I mean, once you have 1, 2, 3, 4, the next step that happens is that you will write I0 again on disk. This is actually the next one that comes after that, right? So bonus question, is there a pattern in this set of files that you will see on disk? Is there any pattern? Can you very easily mathematically characterize the sequence of these files if you say use flags? Yes?
Like binary numbers.
Exactly, it's like binary numbers, except that it's mirror. It's exactly this. Then it means you understand what's going on. You're basically increasing every time. So you start with this, and then 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 this. So you basically see this is the lowest bit here. And if you're mirroring this, you have basically 0, 0, 1, 0, 1, 0, 1. So what am I doing? 0, 1, 0, 0, 1, 1. I'm just taking the mirrored version of that. So you see, I'm just counting in binary. That's all I'm doing. So then you understand logarithmic merging, if you understand that. So now I'm coming back to the slides. So how does it work for the construction? Did we do better in terms of complexity? So now, how many indices do I have? In the first version, I had t divided by n, primary school math. There was n is the size of 1 increment, so we have t divided by n steps in the process, but only 1 index at a time on disk. Here, how many indices do we have on disk? Well, it's logarithmic in t divided by n, right? If you look at the postings, the way it increases there, right? It's logarithmic. Who understands this? It's because we double, right? So if you look at this, imagine that you have a vector with k entries. How many times did you have to double it? It's the logarithm of k, right? That's exactly the same idea. So here we have a list of indices that only grows logarithmically with the number of incoming postings. That's because we double every time, and that's extremely efficient. So we did better, and so the total construction time is now t times log of t divided by n. The new thing is the log. This is the thing we didn't have before. It used to be t times t divided by n. Now it's t times log of t divided by n. Why? Because we have less and less and less merges that have to be done, and less postings that need to get touched. So we have this, but there is a drawback. And what is this drawback? Because as you know, in computer science, there is never a free lunch. We have to pay somehow. We have to give something in exchange for it. What is it? Yes? Search time, exactly. The query time is going to be slower. It's going to take more time. And why is that? Yeah, so you have more standard inverted index to do the union of, right? Instead of having just two, in the original setting you had one on disk, one on memory, it's just one single union. But now you have a union over log of t divided by n. So it's many more standard inverted index, so it grows logarithmically. So it means that the query time is also growing logarithmically. It's no longer just a matter of doing a union. There is a logarithmic growth, and that's the price to pay. We have better construction time and slower query time, right? We have to live with that. So now, in practice, as you probably imagine, because of what I told you regarding the delay even on search engines for indexing websites, periodic index reconstruction is actually something that you find very often in practice. That you keep the old version while you build the new one, and then you drop the old one when you have the new one ready, right? But you probably have noticed now that the indexing is actually less than 2 days, which probably indicates that they also maintain some short-term structure in memory with the new websites. So as you can see, it's a mix of all of these techniques in practice. Okay? So now to wrap up this lecture, so we saw BSBI, SPIMI, MapReduce, and logarithmic merging, so the online index construction. We've done it with the standard inverted index, the plain and simple inverted index, where you have terms and then associated with lists of document IDs. But we've seen in weeks, I think, 3, that we have other kinds of indices as well. In some cases, we want to support phrase search, so maybe we have the locations. So we have also byword indices, when you have several terms here instead of just one. It's a combination of terms. As it turns out, you can very easily adapt them to make it work with index construction as well. You just need to tweak a little bit, but it will work pretty nicely. So you just need to understand it for the standard inverted index and then adapt it for the others. So there was a final consideration, but this is an appetizer for what we will see in 2 weeks in Series 7, is that right now we deal with Boolean queries when we sort the documents here. This is optimized for Boolean queries for the intersection, but we will very soon see ranked queries where we may arrange the documents in a different order. How? We will see in 2 weeks. I think there was also, yes, in the book there's also a paragraph about access control lists. I'm not telling you much about that. It's just that you sometimes, if you are a company and the documents that you are indexing, imagine you're a lawyer company, and some of the documents may be classified in some way, because not all lawyers may have access to all documents. Then you also need to consider, when you construct the index, to make sure that not everybody sees everything. And this is additional complexity in the process, that you need to add some access control lists to the documents and so on. And I cannot emphasize enough how security is an issue. With Spectre, Meltdown, and so on, it's a growing and growing concern for the industry in general. So it will be increasingly present, even when you work in the industry later. This is it for part 5 of the index construction. So we are wrapping up one unit of the lecture here. And now I would like to go to the next part, which is index compression. How can we make these indices smaller? So the first approach that we had with index construction was it's anyway too big, so let's just accept that it's too big and organize the algorithm to make it work with something that's very large. And then you can shard the collection, you can use BSBI, SPIMI, MapReduce, and so on and so on. But can we do even smarter than that, maybe? Maybe we don't need to use all of this complexity in some cases, and we can just reduce the size, be more parsimonious in the space that we are using. So again, a recap. I love doing recaps because it's a way of just repeating and making sure that you remember these things. So the recap is, we've seen Boolean retrieval. We've seen that we have as an input a set of documents that we want to index, and then we have some query. Until now, it's a Boolean query with and, not, or, and so on. Very simple grammar. And the output is a subset of documents that match this query. It's either yes or no. There is nothing else than yes or no, right? Then we've even seen precision and recall. How do you assess that your results are correct and so on. But this is the very simple model of Boolean querying. And the way we do that, we are using some white magic stuff called the standard inverted index that we've seen absolutely every week. And you will see even more of this because this will be all over the place in this lecture. So I don't know if you had enough, if you can't have enough of it, then you will be very pleased to have even more of it now. So we had these search structures. Again, I cannot emphasize enough the hash tables on the one hand. If you don't care about range queries, all you care about is finding a term, or even better, a B+3, which allows you to do range queries. Range queries are especially useful in tolerant retrieval, because remember, for the wildcard queries with a star at the end, this is a range query on the terms. And the same goes for spelling mistakes. If you rotate a bit the words and so on, you can basically come back to a range query. And the B+3s and B3s are very useful for that. And the other argument for the B+3s is that it's very efficient in terms of dealing with disk storage, because the lower part of the B+3 can be stored on the disk, and since it's a very big size, it's compatible with the blocks on disk. So this is why we are not using a binary tree. Okay? So what I'm saying here is that this here has a lot to do with disk access and optimizing the disk access. We've seen these additional features. This is cool stuff that you can then support in your search engine. You can support wildcards, you can support spell correction, and you can support phrase search. Okay? We've seen how to implement. Like, for example, the phrase search feature can be implemented with a by word index. Again, by word as opposed to by gram. By word means that you have these two words here, but it's actually the same as a bigram index, just with words instead of terms. This is why you may hear me sometimes interchangeably use them. If I want to be extremely precise, by word is really the name when you have two terms, and bigram is when you have two letters. Positional index is yet another way of implementing the phrase search feature, where here you don't only have the document ID, so the posting, but you also have the positions in the documents. Okay? So here you can see this is where you have tokens right here, because you have one single posting, but you have several tokens because it may appear multiple times in the documents. I will come back at some point on all these definitions: term, type, document, posting, term. I will do a recap on that so that it's absolutely clear what everything means. We saw the not bigram, but trigram in that case. As I said, gram means letters, so you have all of these indices, and this is used for spell correction and wildcard indices. We've seen term IDs, doc IDs we've seen even before for indexing the documents, but we've seen term IDs, which is a way of having less space while constructing the index in memory. And we've seen ways of building it. It's even still fresh because we did it today. We saw BSBI, blocked sort-based indexing. Sort, so you immediately think of T log T. And then we saw single pass in memory indexing, so you think single pass O of T, linear, single pass. We've seen the auxiliary index. This is in order to build it online. We've seen the simple version with just two indices, one on memory, one on disk. And then we've seen this beautiful generalization that is inspired by the way you allocate memory in vectors with logarithmic merging. And we've seen that the price to pay for this more efficient construction is a slower query time. So this is what we've seen. We've seen a lot, right? That's already quite a lot for a few weeks. And actually, I don't know if it's also visible on the website, but in the way that I have my schedule of lectures, this lecture is actually already in the advanced part of the lecture. The first 5 we've been doing up to index construction, that's what I call basic. It's the basics. And today, it's already what I consider advanced. We are taking it to the next level. So there are several things that I would like to see with you. It's all in the book as always. Term statistics. We are going to do a bit of statistics and analysis and math. So I have terms. A term can be seen as a sequence of characters like ETH, Zurich, computer, information, retrieval. These are all terms. How you define what a term is, we've seen it in week 2. It's not easy at all because there's plenty of things. You can do it very naively with a tokenizer, just tokenizing on spaces, but you have to deal with punctuation, apostrophes, and so on and so on. So it's not trivial. But assume that we've done that. We've tokenized, we've found a way of finding out what the terms are, maybe depending on the language. And now we have a document, and we found a list of terms, a set of terms that this document contains, right? I'm interested in sets. Now I have 2 documents. I'm going to have more terms, probably. More unique terms. Maybe some of the terms are in both documents, so it's not the sum of them, right? But we are going to have more terms if we have more documents. So now, if I try to plot that, the number of terms, distinct terms, against the number of documents, what do you think will happen? Will it be maybe like this? Will it be something more exponential? Will it be something like, I don't know, the square roots? Will there be even a max, that at some point you reach a maximum number of terms because there are only so many words in a language, right? So what happens? Well, I'm asking you. What is this? It's right here. I had to do some neologism here, but it's a good exercise actually if there exists words for that. Anyway, how does the number of terms, which is typically called M in the books, grow with the number of documents in practice? That should actually be a D for documents. How does the number of terms grow with the number of documents in practice? It's all the combinations I showed you on the graph. Is it hyperbolic, but hyperbolic with the horizontal asymptotes, logarithmic, square roots, linear, exponential? What do you think?